can you help me label dimensions? What's that one?
0.03.
Excellent. I've clearly already indoctrinated you guys into accepting bad artwork. What's that one?
2.75.
What's that one?
1 meter.
Oh, yeah. Okay, and so T1 is, I don't know, on the inside and T2 is on the outside, however you want to do this. 0 degrees Celsius and 20 degrees Celsius. Does that make sense?
Yeah.
So can you help me find dq dt?
What's Q?
So 0.02 calories per second per meter per degree Celsius times, what's the cross-sectional area here? The area of interest?
0.03 times 35.
Just 0.75 times the 0.03. Oh my god.
I don't know how you decided T2 and T1 in the first one.
What's the cross-sectional area between T1 and T2?
Oh, why is,
times the height, so
how do you pick T1 and
0.03 times
T2?
0.25.
Say this one, sorry.
Sorry, I just
We want to enjoy our,
Hi, Jen.
Hey, Jen, what's going
Hi, Jen.
we have a special guest visitor. I moved the camera, but I never get it back where I want it again.
Never would. I'm telling you. This worked out great.
Did it?
Yeah.
That's
If
awesome.
I had a key to your office, I'd put it in there.
I'd give you a key to my office, but I can do it later.
It'll be up in my shop. I just want to see how bright it was in here, because I've been hearing stories about how sunny it is in here.
Yes.
Pretty bad, huh?
I like it.
Let's go. All right, good luck, guys.
Thank you, my friend. So, there were a pair of questions. Lorenzo.
Sorry, did ask a question.
Oh, no. Chris,
I don't know how you picked T1 and T2 in the first one.
how I picked them?
Yeah.
I'm just saying, if both of these were at T1, there's no incentive for the energy to flow as heat.
Oh, well, in this case, you said the temperature outside is 20 degrees Celsius, so wouldn't any change, any
Oh.
cross-sectional area in this work?
Well, so you just want to see more of my beautiful artistry.
This one is so bad.
And then for these equations, we don't have to worry about it being in SI units, right?
No.
Right.
I'd have to be some kind of jerk to specifically put on your test that I want it in joules at the end. Oh, wait. I am some kind of jerk.
Oh, wait.
yeah.
That's
Okay.
who you are.
Pause, folks.
Yeah, definitely check to see what kind of units. So out here, in the realm of 3D, is 20 degrees Celsius. But inside that box,
Zero.
you know what it really needs is a handle.
There we go.
That makes a difference.
Okay, open it.
Oh, okay.
Okay, I think
Okay.
that's pretty good. That's pretty good.
Yeah.
A little shading.
No, that's enough.
What we
I
really need is happy little
added
trees.
hinges on it. That's what you do.
So,
Alright, Bob.
so now what?
I guess it's 0.75 meters squared.
So 0.75 meters squared, right?
Alright, but isn't it also 0 degrees? Like if you're saying it's 0 degrees on the inside of that, isn't it also 0 degrees at like the top and the bottom? Oh, I guess not.
No,
I
it's
guess
up
so.
here it would be,
Yeah.
it might be something different underneath, but I specifically asked due to conduction through the door. So. And then temperature, 20 degrees Celsius minus 0 degrees Celsius over the, what's L in this case?
A 1. Is a 1?
0.03?
That's right.
0.03.
Hooray.
Yeah.
Oh, okay.
Someone with a calculator want to bail me out?
375. No. And
Wouldn't L be what or something?
What's the thickness, what's the
Says-
cross section between the surface at T1 and the surface at T2?
It says 10.
0.03.
10 what?
Hours?
Joules per hour.
Calories per second. So we want ice melting per hour, right? So if 10 calories, which way, by the way, is the heat flowing?
Inward?
It's flowing into the old-timey refrigerator. So if 10 calories flow into the refrigerator every second, how many seconds in an hour? 3,600. So I feel confident that I can do this, but feel free to tell me if I get it wrong. I think that would be 36,000.
Yeah. Oh, no.
Yeah.
That's different units.
same. That's kind of
Calories per hour, right?
Oh, okay. Good. You're good.
Yay? But if the ice is at 0 degrees Celsius, we don't have to worry about changing its temperature, but what is the latent heat of fusion?
80 calories.
80 calories per gram. So how do I, so L fusion, H2O, 80 calories per gram. How do we turn 36,000 calories per hour into grams per hour? Yay? And so someone with a calculator help me out?
450?
How many pounds does a kilogram weigh? 2.2 pounds per kilogram. So this is 0.45 kilograms. What's 2.2 times 0.45?
You said 2.2?
2.2 times 0.45.
Like a 1-ish.
0.99? So essentially 1.
So
0.99.
amazingly, It's almost like it was planned this way. If this is the setup of your old-timey refrigerator, you'll lose about a pound of ice per hour. Just by conduction through the door. That doesn't speak to conduction through the sides, so you better make the sides thicker. Right? Why would making the sides thicker help us out here? Come back to our equation.
I'll travel longer.
Bigger one.
If L is bigger, then dq dt is smaller, right? Yay. You could also use a material that has a lower conductance.
So we want our L as small as possible. We want our L as small as possible.
It depends what you're trying to do. If you're trying to pass energy as heat as rapidly as possible, you want L small. If you want to keep that ice from melting, then you want L to be thick. If you try making this door thicker, that would probably help us.
It's just increasing the insulation, right?
How do you go from calories per hour to calories per gram?
Oh, so I'm telling you that the latent heat of fusion for H2O is 80 calories per gram. So you guys helped me get to this idea that through the door is entering by conduction 36,000 calories every hour. And we know that every time we hit 80 calories, we've melted 1 gram of ice. And so that 36,000 calories amounts to about 450 sets of 80 calories. Okay? They all lived happily ever after, at least thus far.
Yep.
Not the poor ice. So that's conduction and conduction type problems. We're kind of all right with that sort of thing. Okay. That time I went with just one vote. Convection is heat transfer by bulk motion of the material, of the medium. And radiation is heat transfer by electromagnetic radiation. So let me use the same language as in my notes. Okay. Let's briefly look at a convective process. Let's imagine that we have a sealed box and there's air inside. And Pictionary team of the day. No? Fire.
Oh, come on.
What's that?
So I say screen.
Oh, ice.
Ice. Susan's on the Pictionary team. The rest of you missed out. You know how fun it is to play Pictionary with old cranky physics teachers. So if there's air inside, as we warm up the bottom, imagine the layer of air at the bottom warms up and expands. As it expands, it becomes less dense. So think back to Physics 130, our discussions of buoyancy. What's going to happen?
It will rise.
Yeah, the less dense stuff is going to rise. Can all the air stay up here at the top? No, so the cooler air is going to get pushed down. We have this convective cycle, right? This can continue because I've added something that's going to hold the temperature at a low value at the top, right? Does that work for you? Okay. I think that I'm planning on coming back to this shortly. Yeah, so we're going to talk about Wien's displacement law. Oh goodness, probably not today. But what I'll tell you is that the greatest intensity of emitted electromagnetic radiation is at a wavelength inversely proportional to the temperature of the object. So my brothers, when they would do something wrong, they had to babysit me. And so one of the things that they would do to try and make sure that they never had to babysit me again is they'd try, hey Mark, you want to go see E.T.? Heck yeah, I want to see E.T. And then we'd be watching Aliens. You know, the tagline might have been in space, no one can hear you scream. They could hear me screaming in that theater. But it seems like in most of the movies they take me to, somehow the thing that was supposed to be scary could like see in the dark, right? And they had some form of like thermal vision. So if we turned out the lights, well, it would still be really bright in here because we have that greenhouse window right next to us. Sweating up a storm for you right now. But imagine that it were dark in here and we turned out the lights, right? Or we could make this room dark. Then I don't emit visible light, at least in any appreciable quantity, right? But I do emit pretty strongly in the infrared. And so does this board, but I'm warmer and the amount scales with T to the 4. And so even though I'm only a little bit warmer than the board, T to the 4 is pretty significant, right? So I shine in the infrared compared to the board. And so if you had night vision goggles, like true infrared goggles, you'd still be able to see me even in the dark, if you could see in the infrared. So the photosphere of the sun, probably you can sound that out from the name, right? Photosphere is the layer of the sun that produces most of the visible light that we get from the sun. It has a temperature, I don't know, 5,782 Kelvin on average. It changes all the time. But you'll hear, 5,800 Kelvin, 6,000 Kelvin, somewhere in that ballpark. I'm perfectly happy. At that temperature, which is warmer than me, right? I'm a few hundred Kelvin, a little bit, I'm around room temperature, right? A little bit above. at the temperature of the photosphere of the sun, it's warm enough that it actually gives out a lot of electromagnetic radiation in the visible part of the spectrum. So just remember, the wavelength is going to be inversely proportional to temperature, but we're going to come back and do Wien's law anyway. So if we wanted to really bad model of the sun, I can't draw the photosphere thin enough, but oh well. I probably could have gone to a different board. I really am only worried about the inner part of the sun for now. So core has a temperature somewhere on the order of about 15 million Kelvin. Very, very, very high. The photosphere temperature somewhere on the order of about 6,000 Kelvin, again, give or take. Oh, goodness. This is a good point for us, because how do you think, what heat transfer mechanism do you think is utilized to get energy out of the core and through the radiative zone? Radiation. So largely ionized convective zone gets to a point where it starts to absorb the electromagnetic radiation. And so what heat transfer mechanism do you think is utilized in the convective zone? Convection. Let's do this. Sorry, my OCD is very calming. I recommend it. It's like adult coloring books. You have warm regions rising, cool regions sinking where they're warmed again, and then rising, break, so on and so forth. Yay? So energy is carried from the inner layers to the outer layers. Photosphere, I think we already talked about this. So the layers outside the photosphere are so sparse. Do you know what I mean when I say sparse?
No.
Not much there. My first apartment was sparsely furnished. So I'm not telling that story. I'm being recorded. You want to hear that story, we got to turn the camera off. But I moved into my first apartment out of the dorms earlier than I expected. I can say that much. And I didn't have any furniture, so.
You can make one with wood and ice.
You didn't do one.
In which class you learned this stuff, Professor?
Uh,
It's astronomy? The sun,
Like
Physics?
I don't remember.
geology.
it's not astronomy?
It might have been. I honestly, for the life of me, I don't know.
That's hard, Professor. Good job.
From art course. Oh, so cool.
All the markers.
This is far more
Like
detailed than
Van
we
Gogh.
expected. Than is necessary.
Yeah, but
Oh, this is so cool. I should teach myself.
So the outer layers are sparse enough that light passes through them without really getting in the way. So most of the light that we get is coming directly from the photosphere. So. Questions, comments, concerns? So
What's the fourth color?
we have radiation, we have convection, we have more radiation, but and then we spent a fair bit of time on convection. I am basically out of time. As always, you guys are awesome. Have wonderful days. Thank you for stopping by. Don't be strangers. Enjoy your days, but not so much. We'll see you tomorrow for labs. It'll be good times.
What's this color?